Hello guys, welcome back to this channel. So in this video, we would discuss a previous year question of GATE DA 225 and it is a linear algebra question. So let's begin. So it is a multiple select question, which means that choose all the correct statements. Option A, Rn has a unique set of orthonormal basis vectors. Option B, Rn does not have a unique set of orthonormal basis vectors. Option C, linearly independent vectors in Rn are orthonormal. And option D, orthonormal vectors in Rn are linearly independent. So you can pause the video to solve, or we can now move to the solution. So let's first see the concepts here and then we will try to solve the question. So one thing here is linear independence. When we have to prove linear independence, what we do? So linear independence, we check for a set of vectors, and a set is said to be linearly independent if summation Ci vi is equal to 0 implies C1 is equal to C2 is equal to dot 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 Ck is equal to 0. What does it mean? So it means that we first uh, take a linear combination of the k vectors. So it means that it becomes C1 V1 plus C2 V2 plus dot 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 Ck Vk. And we equate it with 0. We equate the linear combination with 0. And if and only if we get all the coefficients C1, C2, Ck as 0, then we say that the set is linearly uh, independent. So that is linear independence. Second is a second term which has been used in the question is orthonormality. So a set is said to be orthonormal if for any vector ui uj, ui transpose uj is equal to 1 if I is equal to j, 0 if I is not equal to j. What it means is that if any vector, uh, if we take a dot product of the vector with any other vector, then we get 0. And if we take the dot product with itself, we get 1. So if this property satisfies for all the vectors, then we say that the set is orthonormal. By the way, orthonormality is a specific condition of orthogonality. So orthogonal set is when the dot product gives non-zero or zero. And orthonormality, one more condition is added, which is the non-zero has to be 1. So orthonormal set is a subset of orthogonal set. Okay, so let's see options each one by one. Option A, Rn has a unique set of orthonormal basis vectors. Now this is the statement which has been given. So generally what is the easiest way to solve in these scenarios is that we first try to find counterexamples. So if we are able to find any counterexample, we can say that this statement is false. And if we are not able to do that, then we delve into other methods. So let's see if we can find a counter example for this statement, which means that the statement says that there is only one unique set for a given orthonormal basis vectors. So, for example, for the vector space R2, we have one basis as E1, E2. This is the standard basis where E1 is 1, 0 and E2 is 0, 1. Now we will try to modify it and see if we can get, and this is, by the way, this is also orthonormal. Why? Because if we take the dot product, it will be uh, the zero. The dot product of E1 and E2 will be zero. And it is linearly independent because it is already a basis vector. So it is orthonormal plus basis. First we will try to find the counter example. So how would we do that? We will try to rotate, or we will try to modify this set of vectors and see if we can get another orthonormal basis or not. So one very simple thing we can do is rotate the each of the vectors of the basis. So by rotation is done by multiplying the vectors by a rotation matrix. So here R is the rotation matrix here. And if we multiply each of the vectors, so you can see that earlier this E1 and E2 were like this. And if we rotate it by angle theta, they become like this. So both of these vectors are rotated by angle theta. So B2 will be RE1 comma RE2. Okay. So let's see what we get. RE1 is when we multiply the matrix R with the vector E1, and this we get as cos theta sine theta. Similarly, RE2, we multiply the matrix R with the vector E2 and we get minus sine theta cos theta. So B2 becomes RE1 RE2 is equal to this set. Now we have to check whether this is also an orthonormal basis or not. So checking orthonormality. Orthonormality requires two things. One is orthogonality and another is unit length. Unit length means the dot product of any of the vectors should be 1. So RE1 transpose RE2, that is the dot product of RE1 and RE2 is this cos theta sine theta multiplied by minus sine theta cos theta, and it becomes 0. So since the dot product is 0, we say that it is orthogonal. Now checking unit length. So we will check the unit length of RE1. It becomes mod of cos theta sine theta, and how we calculate the mod is that we take a square root of over the squares of the sum of the squares. So it is root over cos square theta plus sine square theta is equal to 1. Similarly, mod of RE2 becomes also 1. So both are unit vectors. So since orthonormality requires orthogonality and unit vector, and here we have both the conditions satisfied, so it is orthonormal. So what we did is that we modified a standard basis and we still got an orthonormal basis. So at least we have the two orthonormal basis vectors for this R2, and hence you can say that unique orthonormal basis statement is false because there are infinitely many orthonormal basis vectors. We just saw one particular example where we had two basis, and we can also find other basis for the same vector space R2 also, because here theta you can take anything, and by this rotation itself we will get infinite uh, orthonormal basis. So these are the orthonormal basis for this R2. So unique is false and not unique becomes true because we have many orthonormal bases. So options A and B are okay. Let's see option C. Option C says that linearly independent vectors in Rn are orthonormal. So it means that what the statement says that all the linearly independent vectors are also orthonormal in Rn. So we will go by the similar step and try to find any counter example for this statement. The counter example would be, we will try to find linearly independent vectors that are not orthonormal. So since the statement says that all the linearly independent vectors are orthonormal, we will try to find a case where linearly independent vectors set is not orthonormal. So we can again start with the simple standard basis of R2, which is 1, 0, and 0, 1. So this is linearly independent as well as orthonormal. Okay, we know that. Now what we do this, why this is linearly independent? Because if we, yeah, we have seen that if you do the linear combination and equate it to zero, you get the coefficients as zero. And if you take the dot product of each, you get zero. And if you take the dot product of the vectors with themselves, we get the results as one. So what we do is now we will try to just change one element of the second vector and we get 1, 1. So the first vector is same as the in the standard basis. Second vector we change from 0, 1 to 1, 1. Now let's check whether it is linearly independent or not. So again we will do C1 A1 plus C2 A2 is equal to 0, where A1 and A2 are these vectors, and we get C1 plus C2 is equal to 0 and C2 is equal to 0. So C1 is equal to C2 is equal to 0. This means that the coefficients are 0 whenever the linear combination is 0. So this means that the set A is linearly independent. Now let's check whether it is also orthonormal or not. So we will just take the dot product of A1 and A2. So A1 transpose A2 is equal to 1, 0 times 0, 1, and this is equal to 1, and this is not 0. So it is not orthonormal. So we got a basis which is linearly independent and also not orthonormal. So we got a set which has linearly independent vectors but not orthonormal vectors. So the statement C, which says that linearly independent vectors in Rn are orthonormal, is false because we found one of the counter example. So let's now go to the last option, which is orthonormal vectors in Rn are linearly independent. Now, again, we start by the method of finding counterexamples. So first, let's see the statement. The statement means that all the orthonormal vectors in Rn are also linearly independent. Okay, so we have to try to find a case where the vectors are orthonormal, but they are not linearly independent. So we start with our standard basis for R2. So here the set is both orthonormal and linearly independent. Again, we tried by with the set of cos theta sin theta minus sin theta cos theta. We saw in the first option that it is also orthonormal plus linearly independent. Even if we try multiple options, multiple examples, we will not be able to find a case where a set is orthonormal but not linearly independent. Why? Because this statement is actually true. So we will not be able to find counterexamples. So in such cases, when you try too much and you're not able to find the counterexamples, you have to go by other methods. Maybe trying to prove the statement or disprove the statement using mathematical tools. So here actually the statement is true. So we have to prove or we have to check whether orthonormality implies linear independence. We have to check whether it implies or not. So we know that for linear independence, we have to get the coefficients as 0 whenever the linear combination is 0. Okay, so let us assume a 0 linear combination. This is the linear combination C1 U1 plus C2 U2 plus dot 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 CK UK. and it is at 0. So whenever the u1, u2 dot 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 uk vectors are linearly independent, then the coefficients c1, c2 dot 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 ck must be 0. Okay. So what we do is that take inner product with a random vector uj. So inner product of the linear combination with a random vector uj. Uj is again from the same set of u1, u2, u3 dot 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 uk. So you take the linear combination and see what happens. So when we do this, we try to find this linear inner product. What happens is C1 U1 UJ. This is the first term. Similarly, C1 because of the linearity property, this becomes this. So C1 inner product of U1 comma UJ plus C2 inner product of U2 comma UJ and dot 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 CK inner into inner product of UK comma UJ. Now, since the uh, set of vectors u1, u2, u3 dot 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 uk are orthonormal. Why? Because we have to check whether orthonormality implies linear independence or not. So first our case is that the set of vectors u1 through uk is already orthonormal. We just have to check whether it is linearly independent or not. So in this case, all the u1 u dot 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 uk are orthonormal. And so when they're orthonormal, it implies that u1 comma uj is equal to inner product of u1 comma uj is 0. And similarly, of with all the elements except uj comma uj, where it is actually 1. So this inner product will become finally cj. And so inner product of uj with the linear combination is cj. And so you can see that inner product of linear combination with u1 is c1. Similarly, inner product of linear combination, I am writing LC for in linear combination for this whole state expression. So inner product of linear combination with u2 is c2 and so on. Now, this is already 0. Why? Because we are equating it with 0 to check for linear combination. So this is already 0. And inner product of 0 with anything is 0. So this means that Cj is equal to 0. Now, when Cj is equal to 0, it implies that C1, C2, C3, C4 dot 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 Ck are all 0. One by one we can do when we will take the inner product with corresponding u1, u2, u3, u4 and so on. So it means that whenever orthonormality is there, we finally get the linear combination equated with 0 gives all the coefficients are also 0. And so the set is also linearly independent. Hence, every orthonormal set is linearly independent. So we see that in the options A, B, C, and D, only B and D are correct. That is, Rn does not have a unique set of orthonormal basis vectors because it has infinite. And similarly, orthonormal vectors in Rn are linearly independent and not the vice versa. That is, linearly independent vectors are not orthonormal. Okay. So we have this set of takeaways that orthonormality implies linear independence always. Linear independence does not guarantee orthogonality or unit length. And number three, Rn has infinitely many orthonormal bases. Why? Because we can convert the standard basis in, into other orthonormal bases, for example, by rotation or even some other transformation we can apply. So, but there are infinite orthonormal bases possible for Rn. So I'm also attaching a few similarly related questions for the above topics, which can be practiced by you, which can help you understand the concepts even better. So this is the first question. Uh, let V1, V2, V3 let V1, V2, V3 belong to R3, and they satisfy this thing that V1 is perpendicular to V2, V2 is perpendicular to V3, but V1 is not perpendicular to V3. So first two are perpendicular, last two are perpendicular, but first is not perpendicular to last. Which of the following is true? The set is orthogonal, the set is orthonormal, the set can still be linearly independent, the set must be linearly independent. So we will not be discussing solutions to these. Uh, you can solve by themselves. At the end, I have attached a slide of um, hints and answers to these questions, which you can check. So let's move to the next question. Let A be a 3 cross 3 matrix whose columns form an orthonormal set. Which of the following must be true? Option A transpose A is equal to I3. So I here is the identity matrix, and 3 is because it is a I3 cross 3. So it is another notation for I3 cross 3. Option B, determinant of A is equal to 1. Option C, columns of A are linearly independent. Option D, A inverse is A transpose. Let's see the question 3. Consider the following three vectors in R3. V1 is equal to 101, V2 is equal to 110, V3 is equal to 011. Which of the following statements are correct? Option A, V1, V2, V3, the set is linearly independent. Option B, the vectors are mutually orthogonal. Option C, the set can be made orthonormal using Gram-Schmidt. Option D, determinant of V1, V2, V3 is 0. By the way, this Gram-Schmidt is a method which can make any set of vectors as orthonormal. So you can see the slide for the answers and hints. Hope this video was helpful in helping you build the concept related to orthonormality, linear independence, orthogonality, and helped you solve these questions. So let's meet in the next video. Thank you.